Hello and welcome back to my workshop. My name is Shorty Leatherwood, and I put on YouTube a video about cutting gears. The response was pretty good. Upper way, this is not a commercial hob. May not even be construed as a hob to somebody. I used to cut gears like this. This is a gear that actually I cut to replace in my threading kit, because when I made my quick change gearbox I used all the gears out of it, so I had to actually make new gears for it. They work real. Involute gear cutters, single tooth cutters. They were rather expensive. I only bought a few before I realized that I needed to find another way to do this. These cutters right here will cut every tooth number in a range for a diametrical pitch. That's the nice thing about it. They're made from, these are made from W1 or water. We are back at the lathe now. I have installed or chucked up a piece of the 1/2 inch drill rod, approximately 2 inches long with 2 1/4. I wasn't real precise when I cut it. What I want to do now is just face off the end and put a little bit of a chamfer. I'm just going to use a file for that, and then we're going to move this over to the mill actually cut a groove in it, and I'll explain why here just real shortly. We'll go ahead and turn this on and run this now. Got it cleaned up. Something to start with. Okay, I'm back. It actually has been about a week since I made the last segment of this due to work, and yeah, I have to go to work, pay the bills. I was going to show you the tool bit that you're going to use to cut these hobs, and what we're making, or what I'm making here, is an attempt at a 20-degree pressure angle. 20-degree pressure angle, when you cut the tool bit, you need to get a 40-degree included angle on your tool bit. And if you look at this one, if I can get it in focus enough, if you look at this one, you see that it measures 40-degree included angle. In order to get that, I made this little piece. It's got a channel on the back, a little piece that actually fits down on my tool rest in front, and I merely put the tool bit on here, and that holds the angle that I need for this side, and then by simply moving it onto this side, I get the 20-degree on the other side. When I get to that point, I have to get the tip radius correct, and of course to do that it wants to be at a 90-degree angle, so by setting it on the side I do that. You can just hold these up to, you know, at an angle. Welcome back. It's been a long time. I got a couple of nights off here, and I thought I'd try to work on this. I'm not going to be able to get it done tonight, of course, but I thought I'd add a little bit. I want to take just a minute and show you how to line this up, a little cheat way of doing it, a quick way. Works real well with a cutoff tool to get them lined up, squared up, and even. And what I do is I've got my tool bit in here. I'm going to loosen my tool post up, and then all I do is run this in, and using a parallel that normally would be in your vise on your mill, and run this up against the face of your chuck. The chucks are generally fairly, you can use a faceplate, the chucks are generally fairly close, and I find, but if you hold this up here right in line with your tool bit, leaving your tool post loose to swivel, if you'll bring this right up to it, and I'll run this in a little more so it gives us a better square, and you run it right up until it actually squares up and sort of pinches, just very lightly pinches the parallel up against the face of the chuck and up against there. If you're not careful, you can get it off a little bit, but I've got it pretty close right there. And you just want it to just very lightly pinch it where it'll just hold it in place, and then you tighten your tool post down. And by doing that, I've ensured that the tool bit is perpendicular to the surface that I'm going to be cutting, and that way I won't get it off skewed in any way or whatever. Okay, I'm going to put the take the chuck off and put our part back in the thing, get everything set up here for us, and then I'll be right back hopefully, and we'll cut this thing. Okay, I've got it set up in the lathe. I've got it supported by the tailstock. We're going to be doing some pretty heavy cuts here the way that I do this, and it's probably not the best way, but again, it's the way I do it. I'm going to do several things, and I've got this, of course, my machine is CNC. You can do the same thing manually. I wanted to try to do this all as one process. I've actually never done this before as one process through CNC. I normally just set it up and cut several things. First thing we're going to do is I want to cut a little bit of clearance on the end right here. And it's going to come in, actually, I take that back. It's not the first thing it's going to do. The first thing I've got it set up to do is actually skim cut this piece to make sure that it's round. It could be off a little bit, and I don't want to take a chance on that. So it'll actually take 15 thousandths off. It'll come back in and cut this little edge right here. Then it's going to come back after it's done and cut a little bit of relief in the back. Now, one of the things I'm doing is, because I got this set up on CNC, and I don't really want to change tool bits and re-zero everything and do all that kind of stuff, I'm going to cut it all with this tool bit that I have in here, which is my cutter already set up. This cutter doesn't have all the relief angles and everything that a normal cutter that you'd use to turn on a lathe would be, and I showed you that earlier so that it facilitates sharpening this without messing up our angles and all. But because of that, when I'm cutting some of this, it's gonna be taking some pretty hogging cuts, so to speak, for this little machine. So it may sound kind of crazy, but I'm gonna fire this up and see if we can get this to work. Again, I haven't done this before, so it may be a massive mistake. I'm gonna add a little bit of cutting oil as we go, because as I plunge in to make the valley cuts, it's going to be cutting quite a bit. Let's see what we can do here. Let's get the speed right, and then we'll try it. Here we go. Alright, this is going to take the outside cut, and from the looks of it, it's actually pretty round. But I've already got it set up and it's running, so I'm going to let it go ahead and run. It'll take 3 passes. It's only cutting 5 thousandths at a time. The main reason is the way I shape the cutter on the nose, it's a sharp point. There's no radius to it, so it's not going to have a real pretty cut. Smooth finish like you would normally see on one. Okay. Once we get back to the start, it's going to make that relief on the edge right here now, this relief here. The farther in it gets to cutting, it's going to be cutting a large amount off this flank, so ain't no telling what it's going to do. Okay, now we're plunging straight in. I've moved over. I've moved over the 130 thousandths over, and it's making a straight in cut. It's just going way too deep for some reason. Well, welcome back. I had to stop this. Actually, I didn't stop it. I went ahead and let it go on through, but this is the one that came out. And as you can see how thin these are, there was a problem. I went back and checked everything. I thought maybe I was cutting too deep, but after I measured the OD and the ID and then divided that by 2, I found out the depth was correct. I looked at my cutter, and it's extremely hard to measure that tip width, cutter tip width. So I had it a little too wide. When you have it too wide, it's going to create your teeth too thin. If you get it too narrow, it's going to create them too thick. If you're going to make a mistake, probably make a mistake where it's too narrow at the tip, comes too much to a point. And if that case, then you can pull the cutter out, you can grind a little off the very tip of it, and then recut this, and you won't have to scrap it. This one, of course, is no good, but I was going to cut this out, and I said, no, I think I'll leave it in there because I'm only human like the rest of you. It was a first attempt on a full CNC run of a hob, and I'm going to try for attempt number 2. I have narrowed the tip width down a little bit. I think it's a little close to what it needs to be. It's, like I said, it's hard to measure. Maybe one of you out there can send me a video on the best way to measure a tip there. Maybe some kind of quick idea because I'm kind of at a loss at it, but I've narrowed that down quite a bit, and I may even have went too far, and if I did, that's okay, because, again, I can go back over it if I need to. But I'm going to try this again, and let's see if I can do this and get it close to right. Okay, lathe on. Here we go. Again, we're going to make the passes to cut the outside. I probably won't go through the whole thing. I'll more than likely cut out bits and pieces of this so you don't have to watch the whole thing over again. And like I say, when I edit it, I'll try to do that. And you can see the process, but you don't have to watch 3 or 4 passes here. You can just cut back to where they're cutting the other parts. Okay, I'm going to move this carriage out of the way. I'll get to the jog buttons here. Make it a little easier to see. The last step that you need to do on this is actually file. And normally I have a triangular file, but I can't seem to locate it right at the moment. It's probably out in the trailer with the other lathe. Sides. And what it is any burrs that are built up on there, you want to get them cleaned off. A little bit of rounding on that doesn't hurt, and then just take a file across the whole thing, and that will remove any burrs. The burrs will actually make irregular teeth, and you don't want that. Okay, now that should be pretty good there. Looks good. When we return, I'm going to take this over to the mill now, and I'll show you how to cut the actual teeth into it. We'll be using a slitting saw, and I'll show you that next.
Welcome to Aero Gear's program on the installation of bevel gears. For bevel gears to perform properly in a gearbox, certain procedures must be followed during installation. Failing to follow these procedures can result in poor performance or gear failure. The purpose of this program is to provide you with the information you need to successfully install bevel gears. Here's what we're going to cover. First, we'll talk about the specific reasons why proper installation is so important. We'll then talk about mounting distance, marked teeth, backlash, and contact pattern. In this section, we'll be talking about the specific reasons why proper installation of bevel gears is so important. Installing bevel gears is much more involved than installing spur gears. For example, bevel gears must be oriented to each other so that they run smoothly without binding or interference. They must also maintain the correct amount of tooth clearance at all operating conditions. For spur and helical gears, the best orientation normally requires only that the center distance and shaft alignment be correct. No further adjustment is needed. This is seldom the case with bevel gears because the mounting arrangements allow for wide variations in position. All types of bevel gears have an optimum position for best performance. This holds true for straight, xeral, spiral, and hypoid bevel gears. The manufacturer determines this optimum position by running tests on each individual gear set. Several parameters contribute to proper assembly so that the gearbox operates smoothly and efficiently. The most important are mounting distance, matched teeth, and backlash. These parameters will be covered in more detail in subsequent sections. Here's another point to keep in mind. Bevel gears with a quality level of ANSI AGMA Q8 or better are normally manufactured and tested in sets. During manufacturing, the preferred values for each of the 3 key parameters are marked on the individual gears. Also, it is common for the manufacturer to mark a gear set number on each of the 2 gears in a set. Gears manufactured in sets should only be assembled with their mates. This is one reason why, if one gear in a set fails, the entire set should be replaced. The mounting distance of a bevel gear is perhaps the most important parameter for proper operation. Mounting distance can best be defined as the distance from a locating surface on the back of one gear to the center line of a mating gear. The optimum value for the mounting distance is established by running the gear set and adjusting its position to obtain a tooth contact pattern that is consistent with smooth running and optimum load distribution between the mating gear teeth. Because of dimensional variations between parts, each gear in a set has a unique value for the mounting distance, and in most cases, this value is permanently marked on each gear. Here we see a graphic representation of the gearbox. The mounting distance for the gear member is the distance between here and here. The mounting distance for the pinion member is between here and here. To run properly, these distances must be correct. In some cases, the mounting distance isn't easily measured in the gearbox, or the customer needs to change the backlash. This will require verification of the actual contact pattern to ensure the mounting distance is correct. Checking the contact pattern is addressed in an upcoming section. During manufacturing, once the optimum tooth contact is obtained running the parts together, the mating teeth in engagement are marked for identification. Often this is the tightest point of mesh where the normal backlash should be measured. These are considered to be the matched teeth. These marks usually consist of X's or dots on 2 adjacent teeth on one gear and the mating tooth of the other gear. When assembling the gear set, it is essential to position the single marked tooth in the space between the two adjacent marked teeth. Another critical parameter for a bevel gear set to perform properly is backlash. Backlash in bevel gears is defined as outer normal backlash or transverse backlash at the tightest point of mesh. Backlash can be larger at other points of the mesh, but not smaller. Unless otherwise specified, normal backlash is measured normal or perpendicular to the tooth surface. In other words, backlash should not be measured in the plane of rotation. In most cases, the manufacturer marks the normal backlash value on the gear. For the purpose of illustration, we'll show how the backlash is checked in a tester. However, checking backlash in a gearbox is theoretically performed in the same way. The mounting distance of the gears is first set, and the mating teeth are aligned. Then an indicator is placed on the gear tooth surface. Again, the indicator must be located normal to the tooth surface, as is shown here. First, the pinion member is locked, so it will not rotate. Then, the gear member is rocked lightly back and forth. The maximum value on the indicator is considered to be the backlash reading. It's important to keep in mind that the orientation of the tooth to the indicator is essential for obtaining an accurate backlash reading. Here we see the proper orientation. For critical applications where backlash is small, it's a good idea to check the backlash in several areas. Runout from the gearbox's bearings and shafts can change the location of the tightest point of mesh from the matched teeth to another location. An important note here: sometimes it is not possible to locate the indicator normal to the surface, and the backlash measurement must be made in the plane of rotation. Measuring backlash in the plane of rotation will provide a reading that is called transverse backlash. However, this value can be as much as 40% larger than normal backlash. Please contact AeroGear's Design Engineering Department if you need to use this method. When mounting distances have been marked on one or both gears, position the gears with these distances first. Then use the normal backlash value to verify proper assembly. It's important to note, before checking the backlash, at least one of the gears, preferably the pinion, must be installed and positioned at its marked mounting distance. However, it is best to do both members whenever possible. The reason is this: because bevel gears are conical in shape, they can be assembled in an almost infinite number of positions, most of which cause poor performance, while still having the desired backlash value. On gear ratios greater than 1, the pinion position controls the contact pattern more than the gear. The gear controls the backlash more than the pinion. As the ratio increases, the effect becomes more dramatic. 1-to-1 ratio gears control pattern and backlash equally.